Buenos días. En el coloquio del departamento de hoy tenemos invitado, lo voy a presentar en español. Tenemos invitado, yo no estamos. Yeah. Tenemos invitado a George Metcalfe, que vino a trabajar, está trabajando con Miguel y conmigo. Vino por un proyecto que tenemos de la Unión Europea, que bueno, es de CONICET con algunos países de Europa. Él está en este momento trabajando en Suiza, en la Universidad de Bern, y bueno, y está trabajando en temas que están relacionados con lo que hacemos nosotros, que en este caso lo que estamos trabajando son unas semánticas algebraicas para una lógica que sea a la vez modal y difusa. Pero bueno, la charla no la hizo en eso, así que tratado de poner un tema que puedan entender todos, y es sobre deciding equations in order groups and monoids. So, thank you.
Muchas gracias, Manuela. Good afternoon, everyone. So my talk today will be about deciding equations in ordered groups and monoids. That is, groups and monoids equipped with a total order or a lattice order that's preserved by the group or monoid operation. Now, my interest in these ordered structures comes from logic, where they play a key role in representing the semantics of non-classical logics. But of course, ordered groups and monoids appear throughout mathematics, in particular in algebra analysis and topology. To think of some basic examples, you can take the abelian groups of the real numbers or the integers and use the standard order. Now, if you look at the natural numbers, you no longer have a group, because with addition you have not an inverse for every element, but you can order with the standard order this structure and you get what's called an ordered monoid. A more interesting example would be if you take z times z, so the integers as a group times the integers. So you have ordered pairs of integers, and you can totally order this group using the lexicographic order. So you say A comma B is less than or equal to C comma D if A is less than C, or A equals C and B is less than or equal to D. So this is one way to totally order Z times Z. But in fact, there are uncountably many ways to do this, uncountably many total orders on Z times Z. So throughout the talk, I'll hopefully be giving you plenty of other interesting examples of ordered groups and monoids, but I want to start with what's hopefully a quite familiar example. So we look at the ordered abelian group. By ordered, I always mean totally ordered, of the real numbers. Now, what do I mean by this? So I mean a certain structure. So it's the set of all real numbers with the group operations. So in this case, plus, and then the inverse is minus, and the neutral element is 0. But also two binary operations, the so-called meets like this, and the join like this. And these can be thought of as the binary infimum and binary supremum of two elements of the group. Well, in this case, the meet is just the minimum and the join is just the maximum, right? So when you're in a totally ordered setting, these operations are just minimum and maximum. Now, how can we decide if an equation is valid in this structure? And by an equation, I mean, well, built from terms using variables and then the operations of the structure. So you have meet and join, plus, minus, and 0. Well, the first thing to notice is something obvious. If you want to check S equals T, it suffices to check S less than or equal to T and T less than or equal to S. So we can consider inequations instead of equations. And then a first step could be to eliminate inverses from these inequations. So here's an example. So my inequation now is x minus y, meet y, less than or equal to y minus x. Remember that meet is just minimum. And to say that this is valid or holds in or true in R means that whenever I replace x and y by real numbers, this inequality holds, right? So that's what saying that an equation or inequation is valid means. And what I can do is I can just add x to both sides. So I remove the minus x on the right and add y on both sides to remove the minus y. What have we achieved? Well, not much, but we've eliminated inverses from this equation or inequation. And that means that instead of looking at the ordered group of the reals, we can look at the ordered monoid of the reals. We don't have to worry about the inverses. Now, it should be quite clear that there's nothing special about the reals here, except that we want an ordered abelian group. So in fact, given any ordered abelian group, we can reduce checking the validity of an equation in this ordered group to checking the validity of a corresponding inverse-free equation in the corresponding ordered abelian monoid, just by adding on both sides. Of course, this raises the question as what happens when you're non-abelian, and that's something that we'll look at later in this talk. Okay, so we can eliminate inverses, but then we can ask, well, which inverse-free equations are valid in all ordered abelian groups? And there's an easy and well-known answer to this, because it's precisely the ones that are valid in R, so in the real numbers. So to check if an equation holds in all ordered abelian groups, you can just look in the real numbers. But then you can use linear algebra. This is something from first year linear algebra course. You can use Gaussian elimination to just solve the equations or the system of equations. So that's fine. But what about ordered abelian monoids? Well, the first question is, do we have the same valid equations as in the ordered abelian group case? And we'll see that the answer is no. And then the second question is, well, can we decide which equations are valid in all of these structures? And unfortunately, the answer is this is an open problem. There'll be a lot of open problems in this talk. We can move away from the abelian setting and ask, well, which inverse-free equations are valid in all ordered groups? You don't have to be abelian in this setting, or all ordered monoids. Do we get the same equations in these cases? And then finally, we look at the so-called lattice-ordered case. So when we look at a lattice-ordered group or monoid, we no longer require that the order is total. Rather, we require that it's a partial order where the binary meets and binary joins exist. The binary infima and binary suprema exist. A good example of this would be to take, again, z times z, the integers times the integers as a group, but now define a different order where you say a comma b is less than or equal to c comma d if a is less than to c and b is less than to d. So it's like the pairwise order. Well, obviously, this is not a total order, but it is a lattice order. So we'll also look at lattice-ordered groups and then lattice-ordered monoids. So this is the key slide for the definitions in this talk, so please interrupt if something isn't clear. A lattice-ordered group, or L group for short, is an algebraic structure, which just means we have a set or non-empty set and some operations. So in this case, we have binary operations, the meet, the join, the product, a unary operation, which is the inverse, and a constant E. Well, we need a group, right? So if we just take the product, the inverse, and the E, this is a group in the usual sense. If we take the set L with the meet and join operations, we get a lattice. Now, lattices can be defined in two ways. Order theoretically, you think of a poset such that binary, infima, and suprema exist. So then you have the meet and the join. But you can also define them as algebraic structures, as I've written here, where you have these binary operations and they satisfy certain conditions. We need that multiplication distributes over joins and meets on both sides. And that's the definition of an L group. Right? So you have a group, you have a lattice, and this third and fourth conditions relate the lattice order to the group structure. Now, it's not part of the definition, but it follows fairly easily that the lattice is in fact always distributive, which I've written down here. So it just means the meets distribute over joins, binary meets distribute over binary joins, and binary joins distribute over binary meets, exactly as I've written here. And then perhaps the easiest case, at least to understand, is to think of when the order is a total order. So then the lattice is a totally ordered set, and the meet is the minimum and the join is the maximum, and then we call L an ordered group. All right, so we have lattice ordered groups and ordered groups, so a subclass. But now we want to also consider monoids. So let's identify where groups play a role in the name, of course, but also in condition 1. And also it doesn't follow then from the definition that the structure would be distributive. So I want to replace here group with monoid. What is a monoid? It's just where you have a binary operation that's associative and has a neutral element. Right? So every group is a monoid, but not conversely. So the natural numbers with plus and 0, that's a monoid, but not a group. As I say, it doesn't follow from the definition of an L monoid that it's distributive, but we can ask, or we can look at distributive L monoids. And then again, if we have a total order, we call it an ordered monoid. So these are the key definitions. All the classes we'll look at will fit into these in some way. Let's start with the abelian case, because interestingly, this is easier to discuss, but the problems become harder, or generally become harder. So we say an L group or L monoid is abelian, well, if elements permute, right, in the usual sense. So we have an abelian group or abelian monoid. And then we can look at the class of all abelian L groups. And it's well known, as I mentioned earlier, that this has the same equational theory as the ordered group of real numbers, right? Which just means if I look at an equation, S equals T, where S and T are built using the operations of the group and some variables, then this equation holds in all abelian L groups if and only if it holds in R. And the reason we use these wavy equals sign is just to distinguish this from normal equality. This is one case where logicians become very fussy because this is a syntactic object instead of a semantic object. Once you know this, it's not hard to see. Not hard to see that the equational theory is decidable using Gaussian elimination, and in fact, Weiss-Fenning proved that it's co-MP complete. I'm not going to speak about complexity, I'm just going to mention occasionally this is co-MP complete. Let me mention for the algebraists in the audience also some results on representing abelian L groups. These structures have been studied for a long, long time. They were introduced by Dedekind in the 19th century and studied in great detail. And probably the most famous result is due to Hahn, which is that every ordered abelian group embeds into a lexicographic product of copies of R. So you might have R to the n for some n, and then you put the lexicographic order on it, and, well, you look at subgroups, ordered subgroups of this group. In fact, there's a generalization of this to abelian L groups by Conrad, Harvey, and Holland, which says that every abelian L group, that doesn't have to be totally ordered now, is isomorphic to an L group of real valued functions on a partially ordered set. So you think of the functions that go from your partially ordered set, your finite partially ordered set, to the reals. and then you calculate everything point-wise. We don't need these results, but kind of interesting that there's this structure theory that's been developed for these structures. What about the monoid case? So let's look now at abelian distributive L monoids. Well, it's not too hard to show that this has the same equational theory as the class of ordered abelian monoids, so the totally ordered ones. However, there are inverse free equations, L monoid equations, that are valid in all abelian L groups, but not valid in all abelian distributive L monoids. Right? That might not sound so surprising because, well, we're not requiring inverses and all these things, but it's relatively hard to find a counterexample. And here's a counterexample. In fact, it's the smallest one we know, has 9 variables. It's not hard to check that this inequation is valid in all lattice-ordered abelian groups. You can just check it in the real numbers. But you want to show it's not valid in all ordered abelian monoids. And for that, Felix Bou found a counterexample. Okay. Here, okay. This equation fails in a member of the class with 36 elements. And he found this example using a computer program, I think Prover 9. And I guess this doesn't help. So this is the 36 element Cayley table, right, for the multiplication. And he called it an exotic algebra. Okay. More generally, Ribnitsky proved in 1983 that if you look at the equations that are valid in all inverse free redux of abelian L groups, so you just take an abelian L group and you forget about the inverse. Then you look at all the equations that are valid in all members of this class, then this equational theory is not finitely axiomatizable, which means you can't find finitely many equations that derive all the valid equations. You can find a nice infinite axiomatization, and he did it like this. So you take equations of the form S1 meet Sn, less than or equal to T1 join Tm, so that when you take the product, well, so that the SIs and TJs are just monoid terms, so they're only built as products of variables, so that when you take the product of the things on the left and the product of the things on the right, they're the same up to permutation. And we've seen an example already, this 9-variable inequation, because you can see if you multiply the things on the left, you get x1, x2, x3 up to x9. And on the right, you get a permutation of this, x1, x4, x7, and so on. And if you take all of these equations, then you get axiomatization, but of course it's infinite. Okay. Unfortunately, we still have an open problem, which is that the equational theory of ordered abelian monoids, we don't know if it's decidable or undecidable. And of all the open questions I've encountered, this is the most frustrating and puzzling, because these are structures that we encounter all the time in mathematics, and you would have thought that somebody would have come up with an answer to this question. And everything is abelian, right? So it's not that we have the problems of non-abelianness. Maybe just a couple of remarks about this. One way to show decidability is to show the so-called finite model property for your class, which says an equation holds in the class if and only if it holds in the finite members of the class, right? So that's good, because that means you can just look at the finite members of the class. But we know that our class doesn't have this property. We found a counterexample, quite a small one, xy squared less than or equal to e join x squared y cubed is valid in every finite ordered abelian monoid, but not in the real numbers, so not in all infinite ones. I also want to mention a connection to another part of algebra. So this is equivalent, more or less, to deciding if there's a total pre-order on the abelian group of vectors in NK. So you take k tuples of natural numbers with addition, and then 0 is just the 0 vector. So this is an abelian monoid. And then you ask if there's a total pre-order on this, which satisfies finitely many strict inequalities between vectors in NK. So for example, suppose k is 2, then you just have vectors a and b, and maybe you want something like 1, 2 should be strictly less than 5, 7, and 2, 3 should be strictly less than 13, 8, right? And then the question is, can we find a total pre-order on this monoid which satisfies those conditions? A pre-order is where you have its total, but you also have reflexivity and transitivity, but maybe not antisymmetry. So you can have u less than or equal to v and v less than or equal to u for different u and v. That's why it's not a partial order, it's only a pre-order. So I just mentioned that because it connects this question to a question you might encounter in other parts of mathematics, maybe in linear algebra or algebraic geometry. But for us, it's an open problem. What happens in the non-abelian setting? Do we get an improvement? Well, we can axiomatize the equational theory of ordered monoids quite simply. There's a finite axiomatization. However, the equational theory of ordered monoids and inverse free redux of ordered groups are distinct. So again, there's an equation without inverses that holds in all ordered groups, but doesn't hold in all ordered monoids. And we don't know if there's a finite axiomatization of the equational theory of inverse free redux of ordered groups. We suspect that there isn't. But this leads me to, I'm afraid, two further open problems. Is the equational theory of ordered groups decidable? Is the equational theory of ordered monoids decidable? All right, so again, these are kind of quite natural and fundamental questions in mathematics, and it doesn't seem that there's an answer. So we're halfway through my slides, hopefully halfway through the talk, and it's been a bit negative so far, right? Because I've basically said, I've given more questions than answers. So in the second part of the talk, I want to give some positive results by moving to a more general setting. So moving away from total orders to lattice orders. The general case, what about the class of L groups or distributive L monoids? And we're also not assuming abelianness in this case. Let's consider some fundamental examples of L groups. So of course, the reals and the integers and lexicographic products, these are all examples of L groups, but they're all abelian. And you might struggle to think of how a lattice ordered group could be non-abelian. Well, there are some very important examples. Fix what's called a chain, a totally ordered set omega. So it could be a finite set, finite ordered set, or it could be the integers or the reals with a standard order. We have some chain. Now look at all the bijections on that chain that preserve the order. So you have a bijection F such that if A is less than or equal to B, then F of A is less than or equal to F of B. Right? So you can look at the order preserving projections on this chain. You equip it with function composition and you get a group. Because the composition of two bijections is a bijection, the inverse of a bijection is a bijection, and the identity map is a bijection. Moreover, this group can be lattice ordered pointwise. So you take two order preserving bijections F and G, and you say F is less than or equal to G if and only if F of A is less than or equal to G of A for all points A in omega. And then if you're interested in the meet and the join, these are just obtained by taking the minimum and maximum of the points of the values of f and g at each point. So these are nice examples. Maybe to test yourself, think about what happens when you have a finite chain. Maybe you just have a chain with 3 elements. What do you get in this case? Yeah, well, you get one thing, right? You get the identity map. So if you have a finite chain, you just get the trivial L group. What about if you take the integers? Look, order preserving bijections on the integers. The translations. That means that what you get is actually isomorphic to the integers as an ordered abelian group. However, if you take the real numbers or the rational numbers, suddenly you have a lot of flexibility because you can squeeze and stretch intervals in all kinds of ways. Now, these examples are fundamental because of the following theorem due to Holland, which is really the basis for most research into L groups in the last 60 years. It's a kind of Cayley theorem for L groups. It says every L group embeds into the automorphism L group of omega for some chain omega, right? So in a certain sense, if you're investigating L groups, you can look at L groups of order preserving bijections on some chain. They use this to prove that the equational theory of the class of L groups is the same as the equational theory of the automorphism L group of the reals. This automorphism L group of the reals really plays an important role here. And that just means, like in the abelian case, where we have that the reals play this role, here we have that an equation holds in all L groups if and only if it holds in the automorphism L group of the real numbers. And by the way, there are other chains you could take. So the rationals works as well, and there are other examples. The reals are not, they're special, but they're not unique. And then in fact, using this, you can show that the equational theory of L groups is decidable. So this was done by Holland and McCleary in 1979. But shortly, I'm going to give an alternative proof, or at least sketch an alternative proof of this fact. What happens if we move now to distributive L monoids? This is quite nice. We just move away from bijections to order-preserving maps. So the order-preserving maps on a chain equipped with function composition, well, now they form a monoid, but you still have the identity map, you still have closure under composition, but of course the inverses don't exist in general. But we call this end of omega, and this is again lattice ordered in the same way. So this is an example of a distributive L monoid. Now, in this case, you get more. So there are no non-trivial finite L groups, right? So every interesting L group is infinite. But for distributive L monoids, there are interesting finite ones. And I just give you an example here. So let's take the chain with 3 elements, 0, 1, and 2, and look at the order preserving maps on this. Doesn't take long to calculate. There are 10, and they form a lattice which is displayed on the screen here. So what I've done is I've written ijk to denote that 0 is mapped to I, 1 to j, and 2 to k. And of course, there's a restriction. It's not any maps. They have to be order preserving. The bottom element of the lattice sends everything to 0. The top element of the lattice sends everything to 2. When you see lattices displayed in this way, it's very easy to see what the meets and the joins are. Because if you pick 2 elements, the join is here. Not so easy in the infinite cases, but with finite cases, very easy to see what these meets and joins are. And again, these play a pivotal role because we have a version of Holland's theorem for distributive L monoids. Namely, every such algebra embeds into end of omega for some chain omega. And this was proved by Anderson and Edwards in 1984. A very similar kind of result. However, they left open a couple of questions. Is the equational theory of the class of distributive L monoids decidable? And does it coincide with the equational theory of inverse free redox of L groups? Now, for the second question, we might suspect that this shouldn't be the case because we've seen it wasn't the case when we're abelian, and it wasn't the case when we're totally ordered. Also, the first question about decidability, well, these are open questions when we're abelian or totally ordered. But perhaps surprisingly, moving to the non-abelian setting, things become a little easier. So we're going to prove decidability, or at least sketch decidability, and in fact show the equational theory is the same as for inverse free redox of L groups. We start with a finite model property. So for L groups, this would be completely impossible because the only finite L group is the trivial L group. But for this class of distributive L monoids, we have the finite model property, which means if an equation fails in a distributive L monoid, it fails in a finite one. That's what we have to show. So maybe more for the experts, I just sketched the proof idea. Now, the key thing is that because of the Anderson-Edwards result, we can assume that we fail in an endomorphism L monoid, right? So we have a nice representation. So suppose that we fail in end omega for some chain omega, then the key idea is to find a finite subset, omega 0 of omega, so that we fail in end of omega 0. And this will be finite. Well, the first step is to notice that we can assume our equation has a certain form. So I'm not going to go through the details here, but basically we can assume that our equation S equals T can be rewritten as a meet of monoid terms S1 to Sn less than or equal to a join of monoid terms T1 to Tn. This is just kind of basic syntactic reasoning. So we suppose that this inequation fails in end omega. So what does this mean? It means that we have some way of assigning the variables to order-preserving maps on omega such that the inequation fails at some point in omega. So I call it evaluation of the L monoid terms, but it's just assigning to the variables elements of end omega, so order-preserving maps, and some element q in omega, so that these inequalities hold. H of Si of q is greater than HTJ of q, where I is between 1 and n, and j is between 1 and n. And then what we do is we look at the set, and it will be finite, omega 0, which contains all HU of q, where u is a subterm of some Si of Tj. So basically, we focus on the elements we need in omega. And then we obtain our evaluation, which makes this equation fail in a finite distributive model. And so we obtain from this that the equational theory of distributive L monoids is decidable, because in fact, for a given equation, you can calculate how big your finite L monoid has to be, or how big your chain has to be. So you get decidability and in fact co-NP completes. What about the correspondence with L groups? So this is the key fact. The equational theory of this class of distributive L monoids is the same as the equational theory of the class of inverse free redox of L groups. I mean, this inverse free redox is a bit of a mouthful, but it's always just meaning take an L group and forget about the inverse. So perhaps it's a bit simpler to write it this way. S equals T holds in all L groups, if and only if it holds in all distributive L monoids. And I think I won't even go through the proof idea here. The first part is the same as before, but then you step to the automorphism L group of the reals. And in fact, the proof idea here is very sketchy. There's a lot of details in this proof. Right. So what does this tell us? It means if we want to check an equation in distributive L monoids, we can check it in L groups. In fact, we can also go in the opposite direction. But what's the problem? Well, the problem is an L group equation might have inverses. So this goes back to what we saw in the second slide of this talk, where in the abelian setting, we can eliminate inverses. And the key idea is that also in the non-abelian setting, we can eliminate inverses. So I claim, and I won't give a proof of this, but I'll give an example of how the proof works. Take some L group equation, S equals T, then there exists and can be constructed, which is very important for this, a finite set of equations without inverses, so L monoid equations, such that your equation S equals T holds in all L groups, if and only if this sigma holds in all distributive L monoids, right? And I'll give an example in a moment of how this works. This gives an alternative proof of Holland and McCleary's results. The equational theory of L groups is decided and actually also coherent. So how can we eliminate inverses? The abelian setting was easy. We just added things on both sides to eliminate the minuses, right? The idea here is to eliminate inverses by introducing new variables. So this is the key fact that we use. It looks a bit strange. Just to fit things on the slide, instead of x inverse, I write x bar. We have a particular form of equation, E less than or equal to ST join U, holds in all L groups, if and only if E less than or equal to S x inverse join XT join U holds in all lattice ordered groups, right? So the intuition here is that you have ST, and for some reason you want to split it into two. And you can do this using a new variable. The proof of this goes through the fact that you can look at the automorphism L group of the real numbers, but I won't get into it. I want to give an example. So suppose we want to check if this equation is valid in all L groups. And we want to do it by eliminating inverses. Now, what we can't do is just multiply through. Well, we could multiply through by V on the right, but then we would have Z inverse in the middle, which we couldn't eliminate so easily. So what we do is we introduce, using the above equivalence, a new variable x, and then we multiply through by x, actually by xz on the right. So you can see what's happened here is that we've eliminated our Z inverse. We always have a chain of equivalences. But we still have in this equation V inverse. So we need a new variable, which is here Z, not Y. I know, I haven't introduced the new variable yet, because I need to get it into the right form. So I multiply by Z inverse X inverse on the right, on both sides, so that I have E on the left. Now I introduce a new variable, Y, to separate V inverse. Okay, this is getting long now, but I can then multiply through by XZ on the left, and VY, or YV on the right. And what I've got a bigger equation, and now it's got some extra variables, but now I have an equation that doesn't mention inverses. And therefore, by the previous result, we can look at distributive L monoids. Now, although it looks like this equation is growing quite quickly, you can bound the size of the new equation by looking at the size of the original equation. It's just the number of inverses that you want to deal with. Now, one advantage of this is that L groups don't have the finite model property. They can't. Distributive L monoids do. So we can think of there being a kind of finite model property for L groups, but only when we first eliminate inverses. Okay, so actually that is the proof idea for a particular case, but that's exactly the proof. You just have to show that this works in general. So I want to end this talk with a slightly different perspective. If you've had enough, you can switch off now already. This is a different perspective. The point here is that validity in classes of L groups and distributed L monoids has a close relationship to the existence of so-called right orders on free groups and free monoids. And I'll say what these terms mean. So first of all, what's a right order? Well, a right order on a group or monoid is just a total order that is preserved by multiplication on the right. You can define left orders as well. For groups, it doesn't matter which you choose as long as you're consistent, right or left. And you can define by orders to mean it's preserved on both sides. We talk about the positive cone with respect to the right order as being all those elements which are strictly bigger than E. Now, this is only really interesting when you have a right order on a group, because in that case, you can identify your right order, which is obviously a binary relation, with its positive cone, right? So you can think of right orders as positive cones, so as subsets of the group. And in fact, although I don't want to get into it here, it's a big area of research at the moment, is to look at the space of right orders, the topological space of right orders on a group. Actually, they usually use left orders, but it's the same. Or you could look at the topological space of bi orders on the group. Just a couple of remarks here. A group is right orderable. But first of all, to be right orderable, you have to be infinite or trivial. But it'll be right orderable if and only if it embeds into an L group. So this is one of the connections between right orders and L groups. And in fact, a countable group is right orderable, so it has some right order, if and only if it embeds into the automorphism L group of the groups. So this also plays a big role in the study of orders on groups. But what I want to point out here is something different. I want to restrict my attention to right orders on free groups and free monoids. So just to remind you, one way to present a free group over a set X is to think of reduced words over the set X, and then for every variable in X, you take an inverse. So you think of the words that you can build with this, the finite sequences of elements from X and X inverse, but you also cancel occurrences of X inverse. So maybe you have X and Y, your set X, let's say X consists of A and B. Then you also have A inverse and B inverse, and you can look at words over this. So you might have A, B, B inverse, B, and so on. And you cancel all the X inverses and X inverses X. These are called reduced group words. And then the group operation is concatenation plus reduction, because maybe you introduce X inverses. And the empty word is then the neutral element. And what we've proved is that if you have some group terms, so just built using inverse variables and the group operation, then there exists a right order on the free group over X, which makes all these terms positive, if and only if a corresponding equation fails in lattice-ordered groups. So to kind of gloss over the details here, the point is that validity of equations in L groups corresponds to the existence of certain right orders on free groups. And this can be used to go back and forth. In particular, the problem of checking if there exists a right order on a free group whose positive cone contains a given finite set of elements is decidable. So this follows from the correspondence and our previous result. But also going the other way, Clay and Smith proved in 2009 that this problem was decidable. So we could have used their result, or we can use their result, to get decidability for L groups. In fact, their method gives an alternative way of deciding equations in L groups. So just now to mention what happens in the monoid case. So the free monoid is actually a bit easier because then you just look at the words over X. you don't have to worry about cancelling x inverse and so on. And what we can prove is that if you have monoid terms S1 to Sn, T1 to Tm, then there exists a right order on the free monoid over X, which satisfies the inequations Si less than Tj for all I and j, if and only if a corresponding inequation holds in all distributive L monoids. So again, glossing over the details, we have a correspondence between validity of equations in distributive L monoids and the existence of right orders on free monoids that satisfy certain conditions. Now, in fact, this isn't everything. There's a further theorem, which is if you're given some constraints already, S1 less than T1 through to Sn less than Tn, this can also be related to some inequation. But I won't go into the details there. More interesting is the corollary, which was not known in the literature on right orders on free groups and so on, is that every right order on free monoid over X extends to a right order on the free group over X. And if you think about what that involves, it's not at all obvious. So maybe you have, I don't know, 3 letters, A, B, and C, and you look up the free monoid is all the words over A, B, and C, and you manage to find some right order on this. But then the question is, can you then extend that to the free group over A, B, and C? So when you have words that involve A inverse, B inverse, and C inverse, you can. Okay. But we're coming now to the concluding remarks. The key idea, distributive L monoids provide a kind of a finite model property for L groups, and importantly, a route to better understanding their algorithmic properties. So we can prove decidability results by moving to the monoid setting. As we've just seen, the relationship between these two classes also provides a tool for studying right orders on free groups and free monoids. But there are many open questions in the abelian setting and the totally ordered setting. So in those settings, there's a mismatch, which doesn't happen in the L group distributive L monoid case, but does happen when we go to abelian or totally ordered. There's a mismatch between the equational theories of ordered monoids and ordered groups, and abelian ordered monoids and abelian ordered groups, and decidability is an open problem. So if you fancy tackling some interesting and very challenging open problems, these are ones I can recommend, or perhaps not recommend because I got completely stuck with them, but anyway, they're fun to think about. So let me conclude by just putting up the references, and thank you very much for attending my talk. Thank you.
Thank you. Okay, I have 2 questions. One, first of all, if you can say very shortly what is something decidable, because they didn't study.
Okay. Well, I mean, there's the kind of informal answer and the formal answer.
One.
Because the formal one goes through Turing machines or post machines, or you have to study computability theory, and it's hard. The informal one is just that there's an algorithm to decide it. So I think we all know what decidability means, because it means you could write a computer program that would decide your equation or whatever. What's hard, and what you need the formal definition for, is to prove that something's undecidable, because then, how do you prove that there's no algorithm? You need a definition of what an algorithm is. But for positive results, fairly intuitive.
Okay, and the second question was, are you working actually on any of the open problems?
Yeah, I think the abelian case is, let's say, manageable, or, I mean, it's reducible to this problem about finding pre-orders. So then you're just thinking of vectors of natural numbers and trying to find pre-orders on them that satisfy certain constraints. So yes, we are working on it, and Yeah, what can I say other than it feels manageable? Whereas the question with, say, ordered groups, I really have no idea. And anybody that I've spoken to about it, they also don't have an idea. So maybe the answer will be that it's undecidable.
The people that are, I don't know. The people that are in the Zoom, do you want to speak or say something? Okay, then thank you again.
Also, I'm around for another week, so if anybody wants to discuss this or other things in logic, I'm very happy.
Okay, thank you.
Thanks,
Recording.
Okay.